So there are a couple of rules and what I call the basics of potential flow, and that's what we're going to discuss now. Uh, One of the things is that the potential flow follows the principle of superposition. Okay, the principle of superposition works as follows. So we show that the Laplace equation has to be satisfied, right? And in Cartesian coordinates, the Laplace equation looks like this. Given by this, and then in cylindrical coordinates, uh, this is phi. Okay, so this is equal to this in cylindrical coordinates. In polar in Cartesian coordinates, in polar coordinates is actually equal to um, partial of r d phi dr plus 1 over r squared, second partial of phi respect to the squared, plus second partial of phi respect to z squared equal to 0. Okay, so this is cylindrical coordinate. This is uh, Cartesian coordinates. So regardless of how we use this, now let's suppose a solution. There is a solution that is possible to have two possible solutions, right? So we have solution number one, and that's equal to 0. And we also have a solution number two, where it's also equal to 0. So those are possible, right? Since they are possible, and therefore the same flow, then I can basically add these up because I'm adding 0, right? This 0 plus 0 is 0. So if I did this, this is equal to 0, and you can further show that you can actually add the potential flows and set that to be 0. Okay, so if this is true, what you can actually say is the addition of these two would be a new valid flow. And it's a consequence of this, right? So if I had this and I add both of them, that would give me a new valid flow. Okay, so that's the one thing that we have to keep in mind. The second thing that we have to look is what happens in the boundary conditions. Okay, so for the boundary condition, consider the following. We have the boundary, in the boundary condition, we have initial and infinite conditions. So what are the conditions of a solid surface? We got two possibilities. Remember, in a fluid flow, okay, this is a wall, and then we have a condition where it says no slip condition. That means that the flow is going to come, it's going to stick there, it's going to stay there, and you have the slip condition where now all of a sudden the flow is actually going to try to slip. So in this condition is the flow is coming here, right? In the next stage, when it comes here, it just stops at the wall. It just comes and stops. In this case, the flow is coming here, and the next step, when it hits the wall, it does this. It hits the wall, but it keeps slipping, keeps on moving. Got two possibilities, okay? So in the case when there's no penetration, okay, no penetration condition is one that when you have the flow cannot go inside, okay, cannot go through the surface. That's important because in aerospace, when you're working in aerospace, right, you're working in airfoils, you don't want the flow to go inside. You don't want the flow to go inside the airfoil. You want, if this is going, there's a pressure there, there's a flow that's coming here, it's hitting there. You want the flow to stay there, or you want the flow to go like this, right? So here you can say, because of stagnation point, there is a no slip condition because stuck is stuck there, but all the other flow slips around. Okay, so this could be no slipping condition, but we don't want the flow here to penetrate. Okay, no penetration conditions in the airfoil. So in such a case, if that was true, and this is the surface velocity, right? So the velocity of the surface, let's say the airfoil is acting like a rigid body, right? And this is actually moving. What you want to make sure is this is moving at a velocity, and the stream is moving at a velocity. Then what you know is that at the surface, at the point in that surface, okay, at the point on that surface, whatever that surface is, maybe this point in the surface. What we are saying is that the velocity of the surface, the unit normal of the velocity with the dot product with the stream velocity is equal to the velocity at which the surface is moving times the unit vector as well. So, and this is a potential flow, right? But that's the condition. So we are saying that the potential flow times that unit vector is equal to this. So now this is kind of neat, a neat solution, because on the surface, you can show that this is actually the same as the partial of this respect to n. Don't get so scared with n. N is just this direction. Let's suppose this direction, the direction here was x, right? Then this is a derivative respect to x. So then why this is given by this? Because of this. Because when I take these derivatives, pay attention to this. Let me expand on this. So this is suppose phi of x I plus phi of y. Let's suppose it's only a two-dimensional flow, okay, for this example. And the surface is actually y, is going in the x direction. Let's say this is going in the y direction, right? Then the unit normal would be in the I, it will be in the j direction, right? So what you're going to end up then in the problem is a dot product, and you end up respect to y. You see, that's what I mean by n. So that surface, what's happening at the surface is actually equal to the partial of n of my potential flow respect to that n, and that would give you equal to what happens in the velocity at which your surface is moving times the unit norm. Okay. The other thing that you keep in mind is when I talk about initial condition, they really don't exist. The flow does not have any memory. Okay, you cannot have any memory whatsoever of what happens to the flow. The velocity potential for a phi will go from A to B, okay, and it will go A to B, and we know that this is the gradient of phi, and then these are my components in the Cartesian coordinates given this potential flow. Okay, now let's suppose I want to go from point A to point B, and I want to evaluate the line integral of that. Okay, so if I want to evaluate the line integral of the potential now, because remember this is a potential, the line integral of the potential times ds is actually going to give me, because of the virtue of what happens at the boundary, this is the same as the phi ds. Maybe like you can think like ds and ds can cancel out. So you really end up with a, b, d phi, and that gives you phi, and that will give you then what happen, the location in B minus the location in A. Okay? So what this is saying is that this is nothing else in contribution of your potential between 2 points. Is this difference between the potential of the 2 points is the contribution of the circulation along any path. Okay, So that's important for you to learn and understand that, but that's a consequence of the potential flow. This is how potential flows work. So let's understand how the circulation really affects in the potential flow now. And to do that, so what I want you to think in this problem is now, let's suppose instead we have a loop, right? So this was a line that went from point A to point B. So I am saying is that circulation then from point A to point B is the difference of my potential evaluated here and evaluated there, as you can see in this equation, right? The difference is going to give you the contribution of circulation. We have done that in a way. Okay, so now if it's a closed loop, right? So you start at A and you finish at A, then what there are a couple of things that you have to keep in mind, and there are two possibilities, right? Um, no potential flow in a circulation, which we obviously know that's not possible, that's not true, because then if you say I didn't have the potential flow in the first place, this is equal to zero, then really that's kind of the trivial solution. Then uh, the other possibility that we have is that your function phi is actually multivariate if we have a sigma in a potential flow. So what I'm really trying to say is uh, that if this is equal to zero, right, then we actually, in such a case, it's not possible to have a potential flow. Uh, this is really not possible, right? Because then what you're saying this is equal to zero. You don't have any potential flow, which would not make any sense. However, if this is different from zero, then what this really means is that you have a potential flow, but the Stokes theorem cannot be applied. Okay, you remember your Stokes theorem? Just as a review, was equal to the double integral over the surface. Um, right? That's what that's if you remember, that's what it was. So we are saying that that's not possible to apply. You cannot apply that if it's multivariate. You can have more than one value of your function the same point, right? Because as you can see, if this point had multiple points, right, multiple values, then this will never be zero. Okay? So let's keep expanding on this, understanding what is really happening. So when can we have a circulation potential flow? We can have circulation and potential flow when the circulation is different from zero. So what potential flow is saying that your vorticity is equal to zero, right? So if you use the Stokes theorem, you will find that the Stokes theorem would say that the vorticity is zero, so this gives you zero, but it really did not make sense because your circulation is not zero, because the potential function exists and it's unique to the point. Okay, so if the Stokes theorem can be applied, if I can apply the Stokes theorem, okay, the only way I can possibly apply the Stokes theorem is if my circulation is zero. Okay, if the circulation is not zero, then I cannot really apply Stokes theorem. Okay, let's see some consequences of this, some interesting things. So let's see what happens in the potential overflow. And I want you to pay very close attention here. You can pause and take notes here. I want you to consider I have a 3D body. Think about airplane, okay? This could be the airplane. And then you have this flow here around here, okay, A, and then I got a couple of loops. I have a loop A and I have a loop B. Now, if you think about this, these two loops can reduce themselves, right? I can make them smaller, 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 smaller until they become a point. Then this loop, if it can become a point, can be contracted without passing the solid body, then that's called a reducible loop. That loop it is reducible. How about this point? This point, really, the body is here, but it's possible to reduce that to the point, right? I can have a point, and then I can have my body there. It's right and the body, but it's not, doesn't go through the body. So that means it is reducible. Now let's consider this other case, two cases. So now in this case, if you look at it, my loop A is reducible. Why is it reducible? You can see it can contract to the point without going through the body. Now, however, note that a point X and Y cannot be reduced to the point without actually going through the body. Those are called irreducible loops. That means that when I am actually have a potential flow, I can reduce that potential flow only if I don't have a body that I'm going to be, I have to go through it, okay? The consequence of this, the couple consequences, we'll talk about them in a minute. Let's consider another case. Let's suppose this is the fluid and I have another loop there. Now, if you look at it, you know that this is reducible, right? This can be reduced to a point without intersecting your body. However, this loop of the fluid, you can see goes around this, but it is irreducible because the only way I can reduce it is making it go through the body, right? And if it goes, and I don't want it to go through the body, so I will call it reducible. Same thing here. I got this is so this is Y. This is Y. So this is Y and this is A. And now look at A. I can reduce A because it doesn't have to go through the body. But Y, I cannot reduce it because it has to go through the body in order to contract to the point, to make becoming a point. Okay, this is important. The concept of if it can be reduced or it cannot be reduced. Okay, let's continue. Then what we can see is for the 3D body, loop A is reconcilable with B. So look at this. So what he's saying is A is reconcilable with A. So I can combine this with this, right? These two loops could combine together and both can be reducible. Because this is a point, I could join them and the bodies are not affected at all. Now the other case is, as I told you, right, X and Y will be reducible, okay? So the same way you can think, I can combine these two, right? This and this can combine each other without affecting this body, right? So think about this. I got this flow here, right? I can take this flow, and now this flow can be combined with this. I can reconciliate, right? I can do this, right? So now it is possible to reconcile these two loads here, these loops here into one big loop and without affecting the body. I can do that, okay? So now what I cannot do is A plus B cannot be reconcilable with these two bodies. Why? In order to do that, I will have to go through the body or this body, and that's not possible. So that's what it really means by reconcilable and irreconcilable. Okay, so now if a space contains no reducible loops, it's called a simply connected loop. Okay, if a space contains irreducible loop, then it's called doubly connected or multiply connected, depending on the number of irreducible, inconceivable load that may be affected. Okay, so the following, we can do the following conditions, following conclusions. So I can say if my loop is reducible, okay, the circulation will be 0. So if I ask you, what is the value of the circulation here around this loop? It will be 0. It can become a point. This one, it is 0 because it can become a point. This one is 0. But how about this one and this one? No, it's not 0. I cannot make it 0. okay? Um, so gamma circulation may or may not be zero in any irreducible loop because Stokes theorem does not apply. So in this case, I cannot say nothing about these two loops. I don't know what's going to happen with them. Okay, and the consequence of that is very interesting over the airfoil. And we will go with the airfoil now in a minute. Let's suppose my gamma is not equal to zero. Only a doubly or multiply, that can only happen if it's a doubly or multiply connected region. Okay, and gamma 1, gamma x is equal to gamma y. This is circulation around the x. You can see this will be my x. Okay, this is my y. This is my surface y. This is my surface x. So I can somehow make the circle, and I can say, you know what? I'm going to make a circle here, and I'm going to make another one there, but I can go ahead and try to cheat and make this actually go up and make this go down. So when I really add these up, this goes to zero, right? This is going in this direction. This is going in the opposite direction. So when I calculate the circulation, I'm taking the circulation because the circulation goes in this direction. And I keep on going around the circulation. This is one circle. And this one goes down. This one goes in the opposite direction and is coming here. And this one goes up. So that's why this total circulation about the z-axis was going out of the plane. This total circulation would be actually equal to zero because this circulations around these two bodies are zero. This has very nice and interesting effects, and we will talk about that later in the course, and we'll expand on them. But let's do one or two examples to kind of better understand how all this stuff really works.